Okay, so this section we're going to step out of single molecules. Now we're going to start talking about how they interact with other molecules, how they interact in groups. So we started with what is matter, right? And then we were like, oh, it's things like atoms, and we talked about different types of atoms, and we started putting them together, making molecules. And now we're going to start putting molecules together and making things like mixtures or just, solutions or whatever, and talking about their properties. So now we're just scaling up. We just keep getting larger and larger and larger and larger. So, at the beginning of the class, we talked a little bit about different phases of matter, and so we're going to circle back and we're gonna start out there again, refresh everybody's memory, and then work in some new details that I didn't necessarily have at the very beginning, and then we're gonna talk about attractive forces after that. So, there's three primary phases of matter. You've got solid, liquid, and gas, right? There's a few other phases like plasma, what else are there? Glass is actually a phase, so there was a big debate about that for a long time. It literally took someone retiring and then they went, oh, okay, glass is actually a phase of matter. They used to think it was a solid, and then they, because it's solid, right? Like glass is solid. And they decided, oh, it's actually a stressed liquid. So it's a liquid, but if you see an old window, it gets kind of ripply when you look out of it. Things kind of wobble. That's because the glass slowly moves. And so they're like, oh, it's like a liquid. It's just really, 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 really viscous. And so it moves very slowly. Or, that came up with the term stressed liquid. And then it turned out that actually there's some thermodynamic properties that are very unique to glasses. And so, you could make another category here called glass. Or plasma is another one. And that's like, if you ever see a fire, you've seen plasma. That's what it is. So if you're like, oh, what phase is fire? Is it a solid? Is it a liquid? Is it a gas? It's a plasma, which is a lot like gases. So kind of like how glass is kind of like a mix of solid and liquid. Gases are sort of like a mix of liquid and gas in a way. So they're what happens when matter gets really hot, so it's always a high temperature, is that essentially the electrons start leaving the nuclei, so they're not associated. So basically your electron shells just kind of dissipate because the electrons are so energetic that they can't, they're leaving the nucleus, and so you have these nuclei floating around and you just have all these electrons and they're not necessarily associated with each other anymore. That's a plasma. Incredibly reactive. If you've ever accidentally caught your hand in a flame or something like that, you'll realize it's very reactive. And plus the heat too, but we're just going to stick to these three. There's a few other ones too. There's like the Bose-Einstein condensate, comes up from time to time. And I even have a funny story about Bose-Einstein condensate, but I've already gone on long enough here. So, let's circle back. So we've got these three phases of matter, and you can move between them. We talked about this. You can get phase transitions, right? You can see a solid turn into a liquid turn into a solid, gas turn into a solid turn into a gas. And so there's names for this. So when a liquid becomes a solid, we call that freezing. Okay. If a solid becomes a liquid, we call that melting. And you're going to go, oh wow, I'm paying how much to learn this? That's amazing. Wow, an ice cube. When it melts, we call that process melting. Yeah. The liquid turns into a gas, evaporation. Alright. Gas turns into a liquid, condensation. Now these arrows right here, yes, this does happen. You don't see it as commonly, but solids and gases can exchange between each other directly without routing through a liquid. So typically, if you think of like an ice cube, it'll melt and then the liquid water will evaporate and you get a gas. But you can also get a direct exchange between the two under the right circumstances. I'll talk more about that in a second. So if a solid becomes a gas, we call that sublimation, which is a term you might have heard before. And if a gas becomes a solid, that is called deposition. And there's a good chance you've actually witnessed these without realizing it. So I've already kind of talked about this exchange here. You've probably seen condensation sometime or another. If you ever go camping, you wake up in the morning and your tent is all wet on the inside. That is your breath has water vapor in it, and that condenses on your tent. So it's literally your breath that's dripping on you in the morning. You'll never think of camping the same again. Or anytime if you see like a water bottle gets left out in the sun, the water gets hot, but then you start seeing droplets form around the top of the water bottle. So the water is down here, you start seeing drops up here. That's because it's actually condensing at the top. So it evaporates and it condenses and you start to see droplets. If you shake it up, it'll all go back down the bottom, but you get that exchange. So you can see the evaporation too. If you ever boiled water, you're seeing it evaporate, or if you just leave it out long enough, it disappears. It's because it evaporated. Freezing, melting, ice cubes is a great example of that. You put liquid water into an ice cube tray or something, put it in the freezer, turns into solid water, you get ice cubes. But over here, what about these? So sometimes you can see a bunch of fog from sublimation. And deposition is a little trickier. And both of these also take place in your freezer. So if you've ever seen something that gets really freezer burned, all the ice forms on the outside. How does that happen, right? Matter's conserved, so it's not like ice just magically appears. And some of it might be from humidity. That's fair. But it turns out a lot of it is actually the fact that you're... what can we talk about? Like old ice cubes, right? Have you ever seen an ice cube tray that's been in the freezer too long? First off, you don't want those ice cubes because they taste disgusting, right? So you know to toss them. But how do you know? They get about half the size, right? They kind of work their way down. So how does that happen? Sublimation. It's not spilling out as a liquid. It's too cold. But you see sublimation. So when you open the freezer and there's all that fog, that's from sublimation. So all of your items, they freeze. All the water that's in anything that you've put in the freezer turns solid, and that solid slowly starts disappearing as gas, but it will also deposit. And so when you see something that's freezer burn, or if you have an old freezer that doesn't have an auto defrost mode or whatever, or a defrostless freezer, you start losing space because the walls start encroaching. They start getting covered in ice. And it's been a long time since I had one of those freezers, but I remember as a kid we had one, and you have to chip the ice out. You have to unplug your freezer, your fridge and your freezer and everything, and you gotta let the ice melt, and you can kind of like chip it out. Well, my mom got really impatient one day, and she just went in there with the kitchen knife, boom, hit the refrigerant coil in the back of the fridge. The refrigerant gas started going everywhere in our apartment, and she's like, get out, go outside, go outside. So we had to run out as our house filled with refrigerant. The hissing sound, psst. And then we just told the landlord, like, I don't know what happened, and the maintenance guy backed us up, so we just got a new fridge, and we weren't in any trouble, so that was cool. No idea how a knife just randomly punctured. Those old refrigerators, sometimes they just die like that, with a hole through the freezer into the back. Those things happen. But yeah, so that's sublimation, deposition. Those are occurring in your freezer constantly, so that all that ice that's on the outside of whatever's been in the freezer for way too long, like my mother-in-law, her mom passed away, and they went to clean out the house, and there was a ham from, like, I don't know, 1972 in the basement freezer there, because it's the Midwest, so they have a basement freezer, of course. That's what you would think they dug down for frost line reasons. No, it's just so they had more room to put a freezer and store a ham for like 50 years. And so that thing was it looked like a snowball, but then on the inside there was an old ham. And so that was from deposition. Okay, so we can move between these phases, and they kind of each have their own properties. So I'm going to write them down here. Whoops. Solids. Whoa, what's going on there? Too excited thinking about that old ham. It was delicious, by the way. I hope no one ate it. Alright, so solids. They're defined by having a fixed shape and volume, and this should seem familiar. Nothing new there. They are high density, which has some implications we're going to talk about in a little bit. So the molecules are very tightly packed together, and those particles are in fixed locations. They're not moving around. So they're not moving. Okay? And we're just going to say right off the bat that these tend to have strong attractive forces. We'll talk about that more later. And they're kind of low energy. So if you lower the energy, you're more likely to get a solid. Basically, you get it colder, you're more likely to get a solid. Next, we've got liquids. I'll have to write gases like up here or something like that because I ran out of room. It's a lot easier on a board to do this. Okay, so they have the shape of their container, but they still have a fixed volume. So you can have a, shaped like a measuring cup, or shaped like a mug, or shaped like a swan if you have a random swan-shaped piece of, ceramic or something. The liquid just fills the space as given, but it's still a certain amount of liquid. It could be 1 liter, but it could be shaped like this, or whatever. Doesn't matter. Liquids are also high density. So the particles are still close together, but they can move around each other. So they're close, they have neighbors, but they can pass by their neighbors. Whereas in liquid, in solid, they're just locked in, in orderly rows, basically. And so we have a variable shape, as I mentioned earlier. Let's make sure we write that down. And the particles move, but we'll say slow. They slowly move. They're not super fast, generally. Alright, and so then we have gases, okay? There you go. Now it's an organized sheet of paper. How about that? Alright, so gases are going to occupy not just the volume of the container, but the shape. So they're going to occupy the whole thing. Or not just the shape like a liquid, I should say, but the whole volume. So they're going to fill a container. So you always have to store gases in a completely closed container. Whereas liquids, you could have an open top if something doesn't evaporate too fast, and it'll still be there. But gases are, they're gone. So you got to make sure that it is a well-sealed, closed container. And they're going to fill it. And then they're going to take up the whole shape of it too. And so they have the shape and volume of whatever container you put them in. So the shape and volume of container. Alright. And they are low density. But the particles move around, so they're not like stacked around in any way. They're moving around, and they move quickly. So particles move, and we'll say they move fast. Alright, and then what else can we say about these? Oh, yeah, they have the least attractive forces. Alright. So, if solids have the most, gases have the least, guess what that means for liquids? They're right in the middle. So, you got the most attractive forces, the least attractive forces, and you got liquids in the middle. So, these are our properties. And just to compare, see if I can get everything on the screen here pretty well. Gas is a little cut off. You'll just have to deal with that. Solids are nice and stacked and orderly, and the particles don't move around. So you got a particle, you got a particle. They aren't just going to switch. That's not what a solid does. Everything is orderly and in line. So the way I like to think of it is, it's like when you park your car in a parking garage. If it's not where you parked it when you come back later, even if it's just like 2 spots over, if you realize it's 2 spots over, you know something was up, right? It's supposed to not move. Like your car isn't supposed to be parked in a different spot unless you moved it, right? So that happened once with my uncle. He was like, I think 13 or something. My dad's older brother. Maybe he's like 15, I don't know. And he was living back in Ohio, and he went to the store with his grandma, and so my great grandma, and convinced her to leave the keys in the ignition while she went in so he could listen to the radio. And as soon as she was in the store and out of sight, he fired that thing up, took it for a joyride around Toledo, Ohio, and then he got back to the store, and he couldn't remember where she parked it. So, you know, she parked, say, like over here. He probably had some other things impairing his memory at the time, too. Couldn't quite remember where, so he just parked, like, over here. And then he just watched as my great-grandma goes out of the store with her shopping cart, and she's looking for the car, and she's looking for the car. He's just sitting there, doesn't say anything, looking for the car. Starts doing, you have to start doing the search grid, right? You got to start searching the whole parking lot. Eventually, she finds it, and she just goes like, "Oh, I could have sworn I parked over there." And he's like, "Oh, no, I was just sitting here the whole time. No, I don't know what you're talking about. You're getting old, I guess." That's my uncle. I've got some stories about him, but anyway, you know, solid. You don't expect things to move on you. Now, liquids, this is like cars on the highway, right? Or on a road. They're going to follow the shape of the road. You know, you're going to stay within your lines, but you can have passing lanes, right? So you can be going along, and then somebody else just passes you in the passing lane, right? You know, it's like I-5. If you've ever been in a plane, you can always see where roads are because you can see all the headlights, all the taillights, you can see the orientation, and you can see the entire shape of the road. So just like you can see the shape of the container by the liquid filling it, you can see the shape of the roads from cars. And they're not necessarily fixed order. Like, you can have passing lanes, they can pass each other, so on and so forth. So they're moving around. And, you know, there's a speed limit that they're supposed to be following. I think on I-5 it's about 90 miles an hour, apparently. So, you know, there's some rules to it. Now, gases. This is like an off-road vehicle. Or my favorite example is I have a colleague that used to teach in Kansas. And I don't know if you've been to Kansas, but just imagine your countertop, because it's about that flat and about that much stuff on it. So if your countertop had little corn stalks, you've seen Kansas. And he taught in a little town. So he wasn't in one of the big cities like, I don't know, Wichita or something that has like 24 people. He was in a really small town. He taught in a really small community college. And apparently he found out, he was talking to one of his students and found out they'd play this game where they'd get the like whoever had the oldest, most beat up car would take it somewhere. They'd all park it in, like, you know, there's this farmland everywhere. It's like middle of nowhere. And then they would spin a bottle, which they probably already, it was probably full when they got there, and then they drank it down. And they spin it, and whatever direction it pointed, you know, just give it a spin, and like drive that way until you hit something. And they had to go until something stopped the car. It wasn't like, oh, I'm about to hit a tree. They had to go and hit the tree, or, you know, so they'd go through like, be an old barn, take it down, keep going. You know, stuff sometimes gave before the car did, and so that would be a gas. It's just going to go until it hits the wall of the container and bounces off. It's just bouncing around, and it's moving quickly as it can, and that's what they were doing. So they did a great job of modeling gases. Alright, so we're going to introduce the kinetic theory here in a second, but these are kind of the properties, and we'll talk more about attractive forces in a little bit. So just keep in mind that as attractive forces get stronger, you're more likely to have a solid, and as they get weaker, you're more likely to have a gas, and anywhere in the middle, you're more likely to have a liquid. So solid, real strong; gas, real low; liquid, yeah, transitions between the two. And so the kinetic theory of matter is essentially what I described. It's just that particles move, they bounce off each other, they bounce off walls of the container. So a liquid doesn't have enough energy to leave its friends behind. It has some form of attraction to them, thus the name attractive force. And so they all hang out, but they can kind of move around. Solids have a lot of attractive forces, they're locked in. So if it tries to leave, it's really being held back. Whereas gases have very little attraction, they just move around each other. And so again, and this is one of the examples I'm most proud of, is if anyone has ever watched a fight break out in a basketball game, you have seen the liquid to gas transition. Okay? So here's what happens for those of you that are unaware, or if you haven't realized this before. You know, two people get into it, and then everybody on their team holds them back. And basketball players, yeah, it's it's not like baseball where you can be very passive aggressive and like throw stuff at each other. Like you can get really hurt in basketball because you're jumping and you're trusting people to just not chop your legs. So then you land on your head, and then it's happened to somebody at some point or another. And most people have enough empathy to realize like I shouldn't do that to other people. And every now and again, things start to jump off a little bit. But they, they're not football players. They're basketball players. It's a different build, different skill set. Like fighting doesn't really come into it. It's not hockey where it's an instrumental part of the sport. And so everyone just kind of holds back. But every now and again, and so generally they just act like they want to, like, oh, you're lucky these guys are holding me back. 9 times out of 10, that's what happens. Maybe a little shoving, and then everybody like holds everybody back. Every now and again, it's really serious. And somebody actually doesn't just do the token getting held back, they get loose. And so when their friends are holding them back, that's the liquid phase. There's attractive forces. There's movement, so it's not a solid. But there's forces holding back. But then they pop off. They get free of their neighbors, and they're in the gas phase. And then they fight. So when they're fighting, gas phase. When they're getting held back, liquid phase. That's my explanation. So I will close this argument by just saying that there's a really good example from, it was a long time ago. Carmelo Anthony punched someone, I think, on the Knicks. So Carmelo Anthony is an NBA player. I want to say he was on Denver at the time, or maybe he was playing for the Knicks. I don't remember, but he hit somebody, and basketball court's pretty long, and he hit somebody like under this hoop. Something happened, and he punched the guy. Like the liquid failed him. No one held him back, so then you have to look like you're serious. And he punched a guy who was bigger than him. And Carmelo Anthony's not like a small guy, but he hit a big guy. Like this was serious. And then he proceeded to backpedal the entire distance of the basketball court. He went all the way into the tunnel on the other end. I mean, he just kept going and going and going. And so he was in the gas phase, but he was desperately trying to condense back down to a liquid. That's what was happening there. And so you can YouTube it. It's a real thing, really happened. And so you can see what happens when there's a molecule that really wants to be in the liquid phase. Carmelo Anthony did a good job of demonstrating that. He just kept backing him. This guy was serious. So he got held back in the liquid phase, and Carmelo Anthony was desperately trying to condense somewhere over here as far away as possible. He's had an interesting career, Carmelo Anthony. Alright, so that's kind of the kinetic theory. Is just stuff's moving around. Kinetic means motion, just like kinetic energy kind of meant energy of motion. Kinetic theory of matter is just that matter moves around. So solids don't move very much, but liquids and gases do. Gases move around the most. They have the most energy. Solids have the least energy. Liquids are somewhere in the middle. They're always kind of in the middle. Alright, so next we are going to talk about, I'm going to introduce the attractive forces. So this section is going to have a lot of videos because I'm going to really break it up. But we're going to have a video where I introduce different attractive forces and I'll rank them against each other. And then I will make a video for each attractive force where I explain what gives rise to it. And within that attractive force, if you were to see two molecules that have, say, hydrogen bonding, how could you tell which one had more attractive forces? Which one was more strongly hydrogen bonding? Or, how do you decide what's the tiebreaker? So I'm going to do that for all 4 of them. And then I'll have a video at the end on physical properties and a little bit of practice with that. And so this section is going to have a good number of videos, so 7, but I'll try to keep them short. This is a little bit long introduction, at least for the 4 about the different attractive forces. Those will probably combine to be a normal video length by themselves, but I want to keep it chopped up in case you want to review and there's just one you're struggling with. You don't have to keep fast forwarding or rewinding or whatever. Alright.